In previous videos, we went through a revised version of the par inc problem, and we discussed how, with a few twists of the problem statement, that became a nonlinear problem. Specifically, the objective function became a quadratic function. And so in the videos before preceding this one, we went ahead and said, well, what if we just took this objective function here and tried to optimize it, ignoring all the constraints? And we were able to solve it both in Excel as well as in Python using the SciPy package. And we came to an optimal solution. Well, now it's time to actually look at that solution and compare it with the constraints. And we'll do that first graphically, and then we'll work back toward computer solutions that do not use a graphical method. And so first, the formal statement of the problem is shown here. We've got an objective function. X sub s and x sub d, remember, are the quantity of standard and deluxe bags produced. And the difference in what we see here and what we have been seeing throughout the semester is the fact that objective function again has these squared terms in it, which caused this problem to become nonlinear. Now, if you remember back from the very first times we started studying linear programming, we first introduced it with a graphical method. And the same should be able to apply here, right? Just because I've got a nonlinear objective function, I should be able to define a range of feasible solutions with just looking at the constraints here. And so let's first go ahead and do that. We can go through and look at each one of those inequalities, and we come up with this nice blue polygon here, which again is the feasible domain. And so all these real value points inside of the blue polygon would be feasible with respect to those solutions, or excuse me, with respect to those constraints. And then what happens if we put in the unconstrained optimal solution? Well, it ends up being this point right here, this red dot, 600, 375. And the key thing to notice here is obviously it's outside of our feasible region, and hence it is not a feasible solution. We're going to violate the capacities in one of those operations. So if you remember back to linear programming, instead of a dot here, we would have lines, right, associated with the objective function. We started changing the, in this case, the profit, and here we're going to be doing the same thing. We'll change the overall profit that we're setting that quadratic function equal to, and we will start to decrease it down and down and down. But of course, we're not going to have lines, right, because this is not a linear function. Instead, it actually describes an ellipse, and so we will have a series of ellipses that will continue to grow in size. And so that's what I've done here. I've got a little bit of a function here to create the ellipse and a few case examples for the profits. And so we end up seeing something about like this. Or again, that red dot is the unconstrained optimal solution. And then as I decrease the profit, I generate these ellipses. And each time I decrease the profit a little bit more, my ellipse gets bigger and bigger and bigger. And so you almost see this ripple effect, like throwing a rock into a pond, if you will. And what we're looking for is the profit values that at least in some way intersect the feasible region. And that's a similar idea as to what we were seeing with the linear programming. And so if I zoom in here a little bit, you can see a profit of the pink 50,000 is a little high, just barely doesn't intersect the feasible region. But then a profit of 49,500 definitely does intersect the feasible region, has this segment here. And so in this case, we would know that the optimal solution, considering the constraints for this problem, lies somewhere between 50,000 and 49,500, that being the resulting objective function. If we wanted to, we could decrease our step size. Notice here I'm doing step sizes of 500. I could start jumping down to 100 or every 50, and then continue to zoom in my graph and kind of approach an optimal solution graphically that way. That would be one way to get an approximation of the optimal solution. So a few things to notice here before we move on to the analytical, or not analytical, but computer-assisted methods, or we're going to look at how you solve this in Excel as well as in Python. First, that unconstrained point fell on the outside of my feasible region. Well, it would be possible conceivably that that point fell on the inside of the feasible region. If it did that, then we would automatically know that the unconstrained optimal solution also satisfied all the constraints, and our job would be done there. Again, since it is a nonlinear objective function, we're not seeing those lines that we used to see. Instead, we're seeing ellipses, and as we drop down the left-hand side, or what the resulting profit was going to be, we saw the ellipse grow and grow and grow. And again, we're looking for where it intersects the feasible region. Big difference on how it intersects here. With the linear programming problems that we saw, the simplex algorithm basically told us that the optimal solution was going to occur at one of these vertices, right? And so we would only have to check these vertices. Notice here's a good example on the nonlinear side with that nonlinear objective function. The optimal solution obviously is not going to be on a vertices here. It's actually going to occur somewhere right in this vicinity of this line segment, it appears. And so that's one of the more complicating things with these problems is the fact that, hey, I don't just have a set number of these polygon points that I have to test, knowing that I could have a optimal solution occur on a boundary, if you will, of a constraint line, or even inside a constraint line. Or again, if the optimal unconstrained solution also satisfied the constraints. And so that makes things obviously a little bit more complicated from the computational side there. And so with that being said, let's go ahead and solve this problem using Excel as well as Python. And so first, I guess we'll go ahead and use Excel. I believe I already have a workbook started, so we don't have to type too much of the data in here. And so I'll stick it right here. See if I can get it down a little bit smaller and maybe pull up this just a hair. Alright, so there's our model. Here is our workbook, and we want to try to implement the model in the workbook. And so I've just gone ahead and copied the data section down, which has our standard, deluxe, and capacities values in there. And the first thing I'm going to do is talk about decision variables. So this will feel very similar to what we did in the linear programs. And so I'll have standard bags here, I'll have deluxe bags here, and we'll define a few cells for Excel to place the optimal solution at some point. Then I need an objective function. And we want to maximize some value, which represents the total profit contribution. So it'd be negative 1/15 times the number of standard bags squared minus 1/5 times the number of deluxe bags squared plus 80 times x sub s plus, 80 times x sub s. Oh, that's why it's mad. I forgot the squared there. Plus 150 times x sub d. Okay, so with any luck, this objective function here should be now embodied in the formula in this Excel cell on cell C17. And then we go ahead and put in our constraints. And these constraints will be the same as what we've done before. Really the only difference being the fact that objective function is now nonlinear. So we can go left-hand side or right-hand side, a comment, and my comment's really going to be which operation it's referring to. They will all be less than or equal to for us. We'll set the total capacity equal here. That drag down. And what do I want to do? I was hoping to use some product here, but since I've got these as vertical columns and those as horizontal rows, I won't be able to do that so nicely. So I'll just manually enter the first one, and then we should be able to drag if we're careful. It'll be the sum product between these, and when I go to drag, I want to lock C12 and C13. Just like so. And so now we get this relationship up here. Alright, so looking good. Now let's go to our data tab in the solver. Alright, so we want to set the objective as my yellow cell there, C17. I do want to maximize it. I want to allow Excel to modify those cells. And now, unlike the similar problem where we're looking at unconstrained version of it, we want to apply the constraints for our operations. And so I will hit add. And same way you're used to doing it from your linear problems, we'll just add these all in. Okay, make unconstrained variables non-negative, that's great. And yes, we will still use the GRG nonlinear solver. And so I can go ahead and solve this. If you want, you can expose the different reports and take a look at what they have in there. And we said it was somewhere between 50,000 and 49.5, I believe. There was the profit for the optimal solution. Looks like right around 49,920.55, and that optimal solution being right here, 459.7 through 8.2. Obviously, we're doing with standard golf bags, so I don't know if it really makes sense to have fractional golf bags, so you'd probably end up truncating those floating points and arrive at a very good but non-optimal integer version of the solution. There would be the best route to go from this point. But with just floating point numbers, there is your optimal solution. So hopefully that all makes intuitive sense. You can see the workflow is almost identical to what we did in the linear problems, with the exception of picking the solver and then obviously having an objective function in this case that is nonlinear. Alright, so with that being said, I'll go ahead and pull this off to the side. We have been doing stuff in both Excel and Python, so I'm going to go ahead and hop into a little bit of a new notebook here. Slide this one off to the side so we can talk about the Python version. So again, like we've done before, we'll be using the SciPy optimize minimize function. We saw this in the unconstrained one where we passed in a function which described the objective function in our case and gave it an initial start value and had any number of arguments following after that. And specifically what I'm going to look at using is that in conjunction with the linear constraint. Because if you notice in here, there should be a way to pass down the constraints for us. Let's see if we can find a method call here. Right here, yes, are the constraints. Notice it gives us a list of constraints. It's one possible way to do it. And we can look and see how that works. So first I'm going to come down here and we need to do some imports, right? If you look at these from the top, it's SciPy.optimize, and there's a minimize function here, and SciPy.optimize.linear constraint there. Basically what they're doing is describing where in this big SciPy package those two entities are. So I would say from SciPy.optimize import minimize and linear constraint. Alright, so we've now loaded it into this Jupyter notebook here on the left hand side. And so first thing we need is an objective function. So I'll just call it objective func for now. And actually I need one more thing as well. I need numpy in here. This is going to be a numpy array. and it's going to return out a float for us, doing some type hinting. Oh, there we go. And just to keep clear, I think I did this before, but just to make a note for us, we are going to pass into this objective function a NumPy array whose elements represent the number of standard bags and deluxe bags there. So we probably should make some sort of note here just so we all keep track of that. We'll say the standard quantity of standard bags. That's going to represent x sub 0, and the quantity of deluxe bags, that's going to represent x sub 1. So basically we're saying, yes, we're going to pass in a vector of inputs. The first input will be the standard bags. The second input will be the deluxe bags. So with that in mind, again, I can type out this objective function just the way it is first. There's x sub s. There's x sub d. There's x sub s. There's x sub d here. We'll multiply that whole thing by -1. Again, we're doing that because we are trying to use a minimize engine, so to speak. And so if I multiply by -1 on the maximization problem, then I can try to solve for the smallest result of the negative of that objective function, and I should end up with the same optimal solution. Obviously our profit will look negative here, but we know we can just multiply by -1 to invert it. Alright, so that objective function is in our notebook. Everything is happy. And now we'll need to define some constraints, and we'll do one for each one of these. And so first, that first one appears to be the cutting constraint. So I'll say cutting is equal to a linear constraint. And how does it work? We've got linear constraint, we've got a matrix coefficient, a matrix of coefficients essentially here, and then we've got LB and UB, which stand for the lower bound and the upper bound values. Okay. Well, the lower bound and upper bound should be the easy part here. So the lower bound is 0, the upper bound is 630. This part we need to fill in with another NumPy array. So I'll say an np.array. And here I'm going to end up with a list, and the list elements will be the coefficients of my constraint on the left hand side. So something like that. The idea is if I did matrix mathematics, if you will, and multiplied this matrix, essentially vector, since it's kind of one-dimensional in nature, and by this one here that we've described, we would end up with this expression on the left hand side. And so I'll just hit Shift Enter. That looks good. And now we would want to do a similar thing 3 more times. So that second one appears to be sewing. We'll say a linear constraint. It's np.array for the coefficients. It's 1/2 and 5/6. 0 and 600. And then we've got finishing. Again, linear constraint. b.array. 1 and 2/3. 0 and 708. And finally, we have the inspection. I'll also put inspect. Ding equals a linear constraint. It's more np.array. 1/10. Oops. 1/10 and 1/4. 0 and 135. And what did we do? We forgot the parentheses there. Now we're up on the finishing. Oh, I forgot the parentheses and multiple of them. Look at that. There we go. Basically, I'm calling the np.array method to create a NumPy array, and I had forgot the right-hand parentheses there. Alright, so that's looking all good. Now let's see if we can use our minimize function. So again, our minimize function will have the function, the initial guess, those are required, parameters or arguments, and then I have a bunch of options down here, one of which is the constraints. We'll pass in as a keyword. So we'll say result equals minimize, that's the function name. The function is obj_func. We need to give it an initial guess, so we'll just pick maybe 100 and 100. Okay, that is good there. I'll put a comma. Then I'm into the more keyword arguments here, so I'm going to specify as a keyword constraints equal to, it'll be something here, but before I implement that, let's go ahead and put cons, I'll maybe call it. And what I'm doing is I'm just going to load up all of my constraints that I just described inside of this list. So I can just now say constraints equals cons. And now when I hit result, notice I'm getting a successful calculation run. I've been able to determine the optimal solution, it thinks. Then the resulting function, so if I say print resulting profit, we could say what? Result fun times -1. We'll do a little string formatting there. It's 49,920.55. And the resulting values we would enter as results sub x sub 0 and results sub x sub 1. And just for comparison's sake, I believe that is the exact same solution that we have in our Excel file as well. Pulling up Excel here on the right hand side, you can see the objective function 49,920.55 matches, as well as the number of standard bags here and deluxe bags there. So either way you choose, Excel or using Python and the SciPy package, we're able to achieve at the same optimal solution. Alright, and I think that wraps it up for this video. Hopefully you're seeing that there's a lot of similarities between what we were doing before with all our linear problems and these problems. Still the same idea of defining the model and then transferring it in some way to the application that you're using to solve it. Excel is quite similar, where we're just picking a different solver. That in this case we've used the GRG nonlinear solver. And in Python we're doing a little bit different. You're introducing the SciPy package, but hopefully you're seeing that the documentation is good enough that it doesn't leave too many questions unanswered as you're starting to fill out your notebooks.